Before the microwave, reheating one plate of food could become a second round of cooking. Picture an ordinary early 1960s kitchen after the main meal is over. One person arrives home late. The stew is cold, the vegetables are in a covered dish, and the potatoes have stiffened in the refrigerator. To make that dinner hot again, someone must scrape food into saucepans, add a little water, light a burner, stir, and judge when the center is warm without scorching the edge. A casserole may mean heating an entire oven for a single serving. Either way, there are pans to wash and several minutes in which hunger can turn into impatience. Today, the same task may require a plate, a button, and 90 seconds. Yet the first commercial machine sold to do it was almost 6 feet tall, weighed more than 750 pounds, needed water cooling, and cost about $3,000. It looked less like a kitchen appliance than a piece of industrial equipment, because that is what it was. So how did hardware born from wartime radar become a box that could sit on a countertop? And why did its real domestic success come not from replacing the cook, but from rescuing leftovers, frozen meals, and dinners that no longer happened at one fixed time? The origin story offers a simple answer. In 1945, Raytheon engineer Percy Spencer stood near radar equipment. A candy bar melted in his pocket, and the microwave oven was born. The story may preserve a real moment, but it compresses decades of work into a single, sticky accident. It leaves out the British physicists who made compact, high-power radar possible, the wartime factories that learned to manufacture its core component, the engineers who turned dangerous open microwave power into a controlled cooking cavity, and the companies that spent years making the results smaller and cheaper. It confuses invention with adoption. Proving that microwaves could heat food was only the first problem. A useful household oven also needed to run from domestic electricity, cool itself without plumbing, distribute energy through food, stop instantly when its door opened, survive years of use, and cost less than a small car. Then cooks had to learn a new kind of heat. Regulators had to define acceptable leakage, and food companies had to redesign products and packages around cooking times measured in minutes rather than hours. This story follows 3 regions: Britain, where the decisive wartime magnetron was developed; the United States, where radar technology became a commercial oven and safety rules shaped trust; and Japan, where manufacturers helped turn microwave cooking into a mass-produced consumer technology. The central invention was not one metal box. It was the system that finally made that box ordinary. Food had always been reheated, but there was no single universal method. A pot over a fire or stove worked well for soups and stews. Steam, a water bath, or a double boiler could warm delicate food without burning it. An oven could revive a pie or casserole, while a covered pan and a spoonful of liquid protected meat from drying out. Restaurants used warming cabinets, steam tables, and chafing dishes when several portions had to remain ready. These methods were not primitive. They matched the fuels, cookware, meal patterns, and foods around them. Leftovers were also commonly transformed rather than returned to their first form. Cold roast could become hash, bread could enter a pudding, and cooked vegetables could move into a soup or pie. This was intelligent household economy. A new dish disguised changes in texture that slow reheating might exaggerate. But transformation demanded judgment, ingredients, and attention. The cook supplied the temperature control by watching the pan. Hot food remained tied to someone's available time, whether that work was unpaid in a home or counted as labor in a commercial kitchen. Their weakness appeared when the portion became small and the schedule became irregular. A conventional oven heats air, walls, racks, and a large metal cavity before much energy reaches a single plate. A burner directs heat more efficiently, but the food must usually be transferred, watched, stirred, and served from another vessel. The labor per portion rises as the portion shrinks. Reheating a family casserole is one task. Reheating 4 separate plates at 4 different times is 4 tasks. Refrigeration quietly made this problem more visible. Mechanical refrigerators and expanding frozen food markets allowed cooked food to wait safely for another meal and allowed manufacturers to sell dishes that were already assembled. Cold storage reduced waste and loosened food from the season, but cold food still had to cross the final distance back to serving temperature. The refrigerator created a reservoir of convenient food. The kitchen still lacked an equally convenient bridge out of the cold. Electrical engineers had already experimented with using electromagnetic fields as heat. At lower radio frequencies, dielectric heating found industrial uses in materials such as wood, glue, and plastics. Food, however, was an awkward target. Early systems could demand high voltages, produce arcing, or heat unevenly, and they did not offer a practical domestic alternative to a stove. Even Spencer's later patent acknowledged that electromagnetic energy had been used before. His claim was narrower and more important. Much shorter waves in the microwave region could make food heating efficient enough to be commercially useful. That possibility required a source powerful enough to deliver meaningful heat, compact enough to become equipment, and cheap enough to reproduce. Before the Second World War, those 3 qualities did not yet exist together. The domestic problem was waiting for a military component. If you enjoy seeing familiar rooms become historical systems, subscribe. There are more hidden machines waiting behind ordinary habits. Radar works by sending radio energy outward and listening for the faint echo from an aircraft, ship, or coastline. Shorter wavelengths can produce narrower beams and reveal smaller details, but generating powerful shortwave pulses was a severe engineering challenge. In February 1940, at the University of Birmingham, John Randall and Harry Boot operated a new resonant cavity magnetron. Their copper block contained cavities arranged around a central space. Electrons moving through crossed electric and magnetic fields excited those cavities, producing high-power microwaves at a wavelength of roughly 10 centimeters. The magnetron was not the first device to bear that name, and Randall and Boot built on earlier work. What made their version decisive was practical performance. It produced powerful centimetric waves from a device compact enough to support airborne radar. Britain, under wartime pressure, shared the technology with the United States through the Tizart mission in September 1940. The cavity magnetron then became the center of a vast Anglo-American development effort. At MIT's Radiation Laboratory, scientists and engineers created microwave radar systems for aircraft, ships, gun laying, navigation, and weather-obscured operations. Raytheon became a major industrial producer. Percy Spencer's contribution belongs inside this larger machine. He did not invent the cavity magnetron. He was an experienced Raytheon engineer and manager who helped turn magnetron manufacture from painstaking fabrication into high-volume production. Wartime scale also put Spencer beside powerful microwave equipment daily. The candy bar story entered popular culture through accounts published after the event, including a widely read 1958 profile. In that version, a peanut bar in Spencer's pocket began to cook near an operating magnetron. Popcorn followed, then an egg that burst. Later recollections, collected by Raytheon researcher John Osepchuk, describe something less cinematic and more believable as industrial invention. Several people noticed warmth near radiating equipment and chance observations mixed with deliberate experiments. Spencer was crucial because he recognized a product opportunity and had the authority to push it forward. The exact snack that supplied the spark is less secure than the experiment that followed. On October 8, 1945, Spencer filed a patent application assigned to Raytheon for treating food with electromagnetic energy. The document described magnetrons feeding microwave power toward food and explained why wavelengths around 10 centimeters or less could heat it efficiently. The patent was granted in January 1950. Another early Spencer patent showed a conductive cooking chamber and even illustrated popcorn on the cob. These were not recipes disguised as science. They defined the architecture of a new appliance. Generate high-frequency power, guide it into a metal enclosure, place food where it can absorb the energy, and keep the field confined. That final step reversed the logic of radar. Radar sends microwaves into open space and searches for what returns. An oven guides microwaves into a closed space and encourages them to reflect repeatedly until their energy is absorbed by food. Raytheon engineers, including Marvin Bock, helped turn the principle into working apparatus. The company chose the name Radarange, joining the technology's military parent to the kitchen range it hoped to challenge. But radar hardware had been designed to deliver powerful pulses, not to sit quietly beside a sink and produce dinner every night. Sustained cooking generated heat in the magnetron itself. High voltage had to be controlled. Escaping energy could heat human tissue. The very component that had made radar compact would still produce an oven far too large for a home. In 1947, a Cleveland restaurant bought Raytheon's first commercial Radarange for about $3,000. The early machine stood almost 6 feet high and weighed more than 750 pounds. Its magnetron required continuous water cooling, so installation could involve plumbing as well as heavy electrical service. A modern countertop oven can be lifted by one person. The first Radarange was closer to a tall cabinet filled with power equipment, cooling hardware, and a cooking chamber. Judged as a household product, it was absurd. Judged as commercial equipment, it had a logic. A restaurant, hospital kitchen, railroad, or other food service operation might need to heat many portions quickly. Labor and serving time had financial value. The machine could reheat food without waiting for a large conventional oven, and its price could be spread across thousands of meals. Early microwave ovens were also explored for aircraft catering, where getting prepared meals hot quickly was more important than teaching a machine to roast beautifully from raw ingredients. The industry's first attempt to cross the front door shows how much remained unsolved. Tappan licensed Raytheon's technology and, in 1955, introduced the RL-1, the first microwave oven designed specifically for home use. It was dramatically smaller than the commercial Radarange, though still a substantial appliance, about 27 inches in each direction. It required a dedicated place in the kitchen and sold for $1,295, an extraordinary household purchase at the time. Only 34 units were manufactured during the first year. The surviving RL-1 at the Smithsonian reveals the sales problem in physical form. It had a glass-fronted door, adjustable shelf, conventional-looking controls, and a top browning element intended to compensate for one of microwave cooking's weaknesses. Beneath the cavity sat a drawer containing roughly 400 recipes in 18 categories. Tappan was not presenting a leftovers machine. It was teaching buyers to imagine an entirely new range capable of handling a broad repertoire. That ambition collided with the nature of microwave heat. Food could become hot with startling speed, yet fail to look cooked in the familiar way. A conventional oven or skillet heats a surface strongly enough to dry it, brown it, and create roasted flavors. Microwaves deposit energy beneath the surface of food, while the surrounding air and cavity remain relatively cool. Moist food may steam before its exterior becomes hot and dry enough to brown. Meat can be safe and hot, but visually pale. Bread can soften and then toughen instead of becoming crisp. The new oven also broke old cooking instincts. Metal cookware reflected the field and could cause arcing. Eggs in shells and unpierced potatoes could build steam pressure. Thick food needed standing time, stirring, or rearrangement. Sauces could heat faster in one area than another. A cook trained by flame could see the burner and feel the pan. Microwave energy was invisible, and the timer seemed to replace sensory judgment with instructions from a card. This was the first great domestic failure, and it was productive. The RL1 proved that shrinking the cabinet was not enough. A home microwave needed a different power source package, a more forgiving cavity, simpler controls, reliable safety devices, compatible cookware, lower price, and a role that matched what the technology did best. The appliance already existed, the habit did not. To understand the next transformation, follow electricity through a modern oven. Household current enters a high-voltage power supply. That supply energizes the magnetron, a vacuum tube with a central cathode, a surrounding anode block, and a magnetic field running through it. Electrons are pulled outward by the electric field, but bent into curved paths by the magnetic field. As they sweep past resonant cavities in the anode, they bunch together and feed an electromagnetic oscillation. An antenna extracts that microwave energy, and a metal waveguide carries it into the oven cavity. At roughly 2.45 GHz, the electric field reverses direction billions of times each second. Polar molecules in food, especially water, continually try to reorient with that changing field, while dissolved ions also respond. They cannot follow perfectly. The lag converts organized electromagnetic energy into disordered molecular motion. Heat. This is not a special resonance that targets water alone, and it does not cook a thick meal from the center outward. Microwaves penetrate only a limited distance, depending on the food's composition, temperature, and structure. In a large item, deeper regions are heated substantially by ordinary conduction from warmer regions nearer the surface. Ice absorbs microwave energy differently from liquid water, which helps explain why defrosting can produce cooked edges around a frozen center. The metal cavity contains the field, but reflection creates standing wave patterns, regions where the electric field is strong and others where it is weak. That is the physical source of the notorious hot and cold spots. Designers attacked it in two ways. A mode stirrer can alter the pattern by moving a metal reflector, while a turntable moves the food through different parts of the pattern. Either approach averages exposure. Neither makes every food automatically uniform. Stirring a soup and allowing a meal to stand still matter, because heat continues to spread after the magnetron stops. Now reverse that path, and the shrinking challenge becomes clear. Engineers needed a magnetron able to deliver continuous cooking power without the cooling plant of an industrial machine. They needed smaller magnets, compact high-voltage components, fans for air cooling, a waveguide that fit around a useful cavity, and a cabinet that did not become dangerously hot. They also needed a door that could be opened thousands of times while continuing to confine energy. Miniaturization was not simply reducing the dimensions of one tube, it was rearranging an entire power system around domestic voltage, domestic ventilation, and domestic carelessness. Competition widened the engineering base. American firms refined commercial and household layouts. In Japan, Toshiba developed an early microwave oven around 1960. Sharp began mass-producing commercial ovens in 1962, and Panasonic introduced its first model in 1963. Sharp's later turntable model helped make uneven heating easier for users to manage. Japanese manufacturers also expanded magnetron production and export capacity, adding the manufacturing scale and price competition that a global consumer market required. Raytheon took another decisive step by acquiring Amana Refrigeration in 1965. Amana already understood durable household appliances, dealer networks, and service. In 1967, it introduced a countertop Radarange in the United States for $495. This was not the first oven sold for a home. Tappan had reached that milestone 12 years earlier. Its importance was that it brought the microwave closer to a product middle-class consumers could imagine buying without rebuilding the kitchen. The cabinet was compact, but its meaning was still unsettled. Advertisements and cookbooks promoted roasts, cakes, vegetables, fish, and complete meals. Manufacturers naturally wanted their expensive appliance to appear versatile enough to compete with a conventional range. Yet the microwave's strongest advantage was not that it could perform every cooking process. It was that it could deliver heat directly into a small amount of food without preheating a large oven or dirtying another pan. That is the midpoint of the story. The military machine did not win by becoming a perfect miniature stove. It won when an ecosystem of engineers, regulators, manufacturers, cooks, and food companies let it become a different appliance. Its ideal unit was not the family roast, it was the portion. There was still an obstacle inside the product's very name. Microwaves are radiation, and post-war consumers had good reason to treat that word with caution. Microwave radiation is non-ionizing. Unlike X-rays, it does not carry enough energy per photon to remove electrons from atoms, and food does not become radioactive after absorbing it. But non-ionizing does not mean harmless at every power. A sufficiently intense microwave field heats body tissue just as it heats food. A damaged door, failed interlock, or careless servicing could therefore create a real hazard. Early manufacturers used metal cavities, screened windows, door seals, and switches that stopped the magnetron when the door opened. As sales grew, however, confidence could not rest entirely on company assurances. The United States passed the Radiation Control for Health and Safety Act in 1968, providing authority to control radiation from electronic products. A federal performance standard applied to microwave ovens manufactured after October 6, 1971, and the Food and Drug Administration became the central regulator. The standard translated an invisible concern into testable engineering. Before sale, leakage measured 5 centimeters from an oven could not exceed 1 milliwatt per square centimeter. After purchase, the lifetime limit was 5. The oven needed at least 2 operative safety interlocks designed so that one component failure would not defeat them all. A monitoring system had to render the oven inoperable if the required interlock protection failed in an unsafe way. Manufacturers had to certify compliance, supply safety instructions, and maintain testing and quality control programs. These numbers did not make leakage metaphysically impossible. They created a large, enforceable margin below levels known to harm people, while redundant interlocks addressed the most obvious failure, generating power with access to the cavity. Regulation also helped standardize what a safe product meant across competing brands. Trust was not merely advertised, it was embodied in door geometry, switches, test loads, measurement procedures, labels, factory records, and the possibility of recalls. Even the viewing window became a lesson in controlled invisibility. A perforated metal screen lets visible light pass, while reflecting microwaves whose wavelength is vastly larger than the holes. The user can watch the food without opening the electromagnetic enclosure. In modern use, the FDA reports that most microwave oven injuries are thermal burns from hot containers, overheated food, or erupting liquids, not injuries from radiation. The old fear was not imaginary. It was engineered into an increasingly uncommon failure. Public concern did not disappear instantly. Consumer testing in the early 1970s continued to question emissions and the adequacy of available knowledge. Nor did federal rules alone cause adoption. Prices had to fall, products had to become reliable, and service networks had to mature. But by formalizing a safety flaw, regulation removed one source of uncertainty, just as mass production was attacking cost. The price change was dramatic. The Smithsonian notes that by 1976, a new microwave could cost less than $300, and the appliance was appearing not only in kitchens, but in dormitories, offices, and break rooms. In 1992, the United States Census Bureau found that 73.8% of households owned one. By 2000, the Smithsonian reports, the figure had reached about 90%. This was not a universal global timetable. Adoption varied with household income, electric service, kitchen space, local food habits, and the availability of prepared foods. But in markets where those pieces aligned, the microwave moved from futuristic spectacle to background infrastructure within a generation. The final barrier was on the plate. A microwave could heat a frozen dinner quickly, but the classic aluminum tray reflected its energy. In the 1980s, Swanson shifted its frozen meals into plastic trays as microwave reheating became more common. The change sounds trivial, yet it joined the oven to the freezer aisle. Food no longer had to be removed from the package designed for a conventional oven. The package itself became part of the cooking system. Product development accelerated. Pillsbury introduced a line of microwavable foods in 1976. According to the National Museum of American History, food companies released more than 760 new microwavable products in 1987 alone. Engineers developed expanding popcorn bags, vented films, compartmented trays, and crisping sleeves. Some packages used a thin, microwave interactive layer called a susceptor. Instead of allowing all the energy to pass into moist food, the susceptor became hot and supplied intense surface heat, helping popcorn oil warm efficiently or giving selected foods a browner, crisper exterior. Microwave popcorn became a compact transgender of this partnership. The bag had to store kernels, oil, and seasoning, expand under steam without bursting, concentrate useful heat, and tolerate ovens with different field patterns and power levels. The product was not simply popcorn placed near a magnetron, as in the laboratory legend. It was a snack whose container performed part of the cooking. The food had to be engineered as carefully as the box. Portion size, shape, salt, water, fat, starting temperature, and arrangement all changed how energy was absorbed. Instructions began to specify oven power, stirring, rotation, puncturing, covering, and standing time. A meal that appeared to require 3 minutes could need an additional minute at rest so heat would travel into cold regions. The timer on the front of the oven was only one part of the recipe. This new market also exposed the mismatch between the dream sold in early cookbooks and everyday use. Manufacturers had demonstrated that a microwave could cook ambitious dishes, and writers continued to develop serious microwave cuisine. But later use studies repeatedly found that simple, medium, or low complexity tasks were central. Reheating leftovers, warming drinks, defrosting ingredients, melting butter, and preparing packaged foods. The appliance was used frequently precisely because each use asked so little. That changed domestic time more than it changed the world's menu. A child could heat one portion after school. A shift worker could eat a hot meal after everyone else had finished. An office employee could turn a refrigerated container into lunch without a staffed kitchen. Leftovers became easier to use because reheating no longer imposed the labor of another full cooking session. The microwave did not single-handedly create irregular schedules, dual-income households, convenience food, or solitary eating. Those trends had broader economic and social causes. It did, however, make separate mealtimes materially easier. Convenience carried costs. Single-portion foods encouraged more trays, films, sleeves, and bags, many intended for one use. A machine that could save energy by heating a small portion instead of a large oven could also support a more packaging-intensive food system. The microwave removed friction from the last few minutes of a meal. It did not remove the factories, plastics, refrigeration, transport, and waste behind that meal. Press the button today and an invisible chain comes to life. The electrical grid supplies the pulse of energy. A high-voltage circuit drives a descendant of the wartime cavity magnetron. A waveguide directs power through a frequency band reserved for industrial, scientific, and medical use. A metal chamber, stirrer or turntable, screened door, and redundant interlocks manage the field. Federal standards define acceptable leakage. Global factories provide components. The refrigerator and cold chain keep the food ready, while packaging engineers decide how steam escapes and where the surface becomes crisp. Remove any major link, and the famous convenience changes. Without electricity, the oven is a sealed cupboard. Without refrigeration, many leftovers and frozen meals cannot wait safely. Without standardized containers and instructions, speed becomes unevenness or burns. Without manufacturing scale, the machine returns to the economics of the 6-foot Radarange. The countertop box feels independent only because its dependencies have become reliable enough to disappear. Those dependencies also explain why the microwave's history cannot stand for every kitchen. Where electrical service is unreliable, household income is lower, prepared food is less available, or meals are cooked communally in large vessels, a fast single-portion oven may solve a smaller problem. Even where the machine is common, it complements kettles, pans, rice cookers, grills, and conventional ovens rather than replacing them. Its success is specific. It removes waiting and supervision from certain heating jobs extraordinarily well. That specificity produces a double result. For a small serving, direct microwave heating can use less energy than warming a full conventional oven. Yet the same convenience supports single-use trays, films, crisping sleeves, and a global frozen food chain. It can preserve leftovers and reduce one kind of waste while creating packaging waste somewhere else. Like the radar system from which it descended, the microwave is efficient because a much larger network has decided exactly what task it should perform. So how did a massive commercial installation with water cooling become a safe domestic appliance? Not through one melted candy bar and not through miniaturization alone. Wartime radar supplied a powerful magnetron. Engineers converted pulses and open beams into sustained heating inside a controlled cavity. Appliance makers reduced size and price. Regulators made safety measurable. Manufacturers in several countries scaled production. Cooks learned the limits of invisible heat. Food companies redesigned meals and packages around the machine's greatest strength. Heating one portion quickly. Return to that late plate in the early 1960s kitchen. The stew no longer needs a saucepan. The casserole no longer requires a full oven. And the person arriving after dinner does not need someone else to restart the kitchen. The small beep at the end sounds like an appliance finishing a task. In fact, it is the audible tip of a system built from radar physics, mass production, regulation, refrigeration, and a new idea of mealtime. The microwave did not conquer the kitchen by learning to make dinner. It conquered it by learning that dinner does not always happen at the same time.